The year is 1943. In the smoke-filled, map-lined war rooms of Norfolk House in St. James's Square, London, the Allied planners of the Supreme Headquarters Allied Expeditionary Force, or SHAEF, are finalizing the details for the largest amphibious invasion in the history of warfare, Operation Overlord. The air is thick with the smell of stale tobacco and nervous sweat. Generals and admirals are poring over title charts, lunar cycles, and reconnaissance photos of the Atlantic Wall. They are choreographing the movement of 150,000 men and 20,000 vehicles across a hostile sea, a logistical ballet of unprecedented complexity. But beneath the tactical planning, buried in the logistical appendices of the invasion documents, the dull, unglamorous spreadsheets that win wars, lay a strategic problem so immense, so chemically volatile, that it threatened to sink the entire operation before the first boot touched the sand of Normandy. That problem was not ammunition or food or even the resolve of the soldiers. It was oil. Modern mechanized warfare, the kind required to break out of a beachhead, race across the hedgerows of France, and defeat the highly mobile Wehrmacht, is fueled entirely by petroleum. The Allied war machine was a thirsty beast, a combustion engine army unlike any force previously assembled. A single armored division, on the move, consumed 300,000 gallons of gasoline per day. The logistical projections for Operation Neptune, the naval component of the invasion, estimated that the Allied forces would require approximately 3,000 tons of fuel every single day in the initial phase alone. As the armies grew and moved inland towards the Rhine, that number would skyrocket to millions of gallons a week. The traditional logistical solution to this demand was terrified, fragile, and inherently vulnerable. The standard doctrine called for fuel to be shipped across the English Channel in coastal tankers, slow-moving vessels that were essentially floating bombs. These ships would have to navigate minefields, dodge E-boats, and then offload their cargo into temporary storage facilities, essentially giant rubber bladders on the beach. From there, the fuel would be laboriously transferred by hand into 5-gallon jerry cans. These millions of steel cans would then be loaded onto trucks and driven to the front lines over cratered, refugee-clogged roads. This system was a logistical glass jaw. It relied on a sequence of miracles. It required capturing a deep-water port, like Cherbourg, almost immediately to handle the heavy tankers. But the Germans were experts at demolition. The Allies knew from intelligence reports that any port they captured would likely be mined, blocked by sunken ships, and utterly wrecked. Furthermore, a tanker sitting in a crowded port was a sitting duck. The German Luftwaffe, though weakened, could still mount raids. The Kriegsmarine's E-boats were prowling the channel at night, and looming over everything was the new terrifying threat of the V-1 flying bomb and the V-2 rocket. The logistical experts calculated that a single well-placed torpedo or bomb hitting a fuel tanker in a crowded harbor could cause a chain reaction that would incinerate the supply head, destroy the docks, and cripple the entire invasion force for weeks.
General Dwight D. Eisenhower faced a nightmare scenario. The troops land, they fight their way inland, and then 10 or 20 miles from the beach, the tanks sputter to a halt. The engines go silent. The operational pause that would follow would give the Germans exactly what they needed: time to bring up their Panzer reserves, counterattack against a stationary enemy, and push the Allies back into the sea. The question wasn't if the Allies could land their troops, but how long they could fight before the physics of fuel consumption strangled them. The ghosts of Dunkirk hung heavy in the room. The audacity of the eventual solution originated not with an engineer, but with the combined imagination of two men who refused to accept the limitations of conventional logistics: Admiral Lord Louis Mountbatten, the Chief of Combined Operations, and Geoffrey William "Billy" Lloyd, the British Secretary for Petroleum. Mountbatten was a man who specialized in the impossible, a leader who viewed engineering constraints as mere suggestions. Faced with the looming fuel bottleneck, he realized that ships were the weak link. The weather in the Channel was notoriously unpredictable and could stop tanker traffic for days. U-boats could sink them. He needed a method of delivery that was weatherproof, bomb-proof, and continuous. In April 1942, during a demonstration of flamethrowers, he famously turned to his planners and asked a question that sounded like science fiction. Could we lay a pipeline across the English Channel? The idea was met with the expected blend of enthusiasm from the dreamers and utter skepticism from the experts. Critics, especially from the shipbuilding and oil industries, said it was a pipe dream. Literally. The English Channel is a chaotic body of water. It is swept by ferocious tidal currents that scour the bottom. The seabed is a graveyard of jagged rocks, centuries of shipwrecks and shifting sandbars. The salt water is highly corrosive to steel. A pipeline was fine for the static deserts of Iraq or the plains of Texas, but under the abrasive, pressurized salt water of the Channel, a standard steel pipe would kink, burst, or simply be destroyed by the first passing ship's anchor or trawling net. Despite the skepticism, the strategic necessity outweighed the engineering risk. The project was immediately greenlit, cloaked in absolute secrecy, and assigned the simple yet deceptive code name PLUTO, Pipelines Under the Ocean. It was a project that would require the resources of a nation and the silence of thousands of workers. The task of making the impossible reality fell to Arthur Hartley, the chief engineer of the Anglo-Iranian Oil Company. Hartley was a pragmatist. He knew that rigid steel pipes, of the kind used in oil fields, were impossible to lay in a combat zone. You couldn't have a lay barge sitting stationary in the Channel for weeks, welding sections together while German coastal artillery rained shells down on it. The process was too slow and the target was too big. To lay a pipeline across 70 miles of ocean while under potential enemy fire, the pipe had to be flexible. It had to be unspooled like a fishing line from a moving ship, not built like a bridge. Two competing revolutionary designs were developed in parallel, driven by the urgency of the war.
The first design was the HAIS pipe, named after its inventor, H.A. Hammack, of the Iraq Petroleum Company, combined with the manufacturing might of Siemens Brothers. This was not a pipe in the traditional sense. It was a masterpiece of composite engineering. Hammack looked at the massive undersea telegraph cables that connected continents and realized the answer lay there. The HAIS pipe was essentially a hollow submarine cable. It started with a lead core, a continuous lead tube, extruded in one piece that was flexible and chemically inert to petrol. But lead is soft. The internal pressure of the fuel, pumped at 1,500 pounds per square inch, would blow it up like a balloon. So the lead was wrapped in layers of asphalt-impregnated paper and cotton tape to cushion it. Then came the armor, 4 layers of high-tensile steel tape wound spirally around the core to prevent it from bursting under the immense pressure. Finally, the whole thing was wrapped in a layer of jute and heavy galvanized steel wires to protect it from the abrasion of the seabed. It was 3 inches in diameter, incredibly heavy, yet flexible enough to be coiled. The production of the HAIS cable was a logistical feat in itself. Existing cable factories were commandeered. Lead presses ran 24 hours a day. But there was a catch. The presses could only produce lead tubing in specific lengths. The engineers had to develop a way to join these lengths without creating a weak point that would burst under pressure or snag during deployment. They created a special coupling, a high-tech splice that was swaged onto the lead and then rearmored, allowing the cable to remain continuous and flexible. The second design was a gamble on metallurgy, developed by engineers B.J. Ellis and H.A.L. Fisher. It was known as the Hamel pipe. This was a 3-inch diameter steel pipe, but it was unlike any steel pipe ever made.
It relied on a specific, highly flexible grade of steel. The walls were relatively thin, allowing the pipe to be welded together into massive links and then wound onto a drum. The challenge with Hamel was that steel, unlike the composite HAIS cable, became rigid once it was bent. It hardened. To use it, the engineers had to rely on a massive, floating deployment system that could unspool it under tension without snapping it. By 1943, British factories were humming with the production of these experimental lines. But the immediate problem wasn't just manufacturing the pipe. It was the method of deployment. You could not lay 70 miles of heavy pressurized pipe from a standard barge. It would take weeks, and the pipe would tear itself apart in the swells. The deployment had to be continuous. Once the ship started moving, it could not stop until it reached France. For the HAIS cable, the solution was relatively straightforward. The Allies converted a merchant ship, the HMS Latimer, stripping out its hold and installing a massive cylindrical tank. The cable was coiled inside this tank like a garden hose, layer upon layer, mile upon mile. When the ship moved, the cable would peel out of the hold, run over a massive wheel on the bow, and sink to the bottom. But the Hamel steel pipe required something far more radical. It required a machine that looked like it belonged in a Jules Verne novel.
The solution was the conundrum. The conundrum was a gargantuan floating steel spool. It was a drum over 90 feet long and 40 feet in diameter. When fully loaded, it weighed 1,600 tons. It was designed to resemble a massive cotton thread reel floating in the water. Each conundrum could spool up to 70 miles of the flexible Hamel steel pipe. The idea was simple but terrifying in scale. The conundrum would be towed behind a tugboat. As the drum rotated in the water, the pipe would unwind and lay itself on the seabed. The engineering required to build the conundrums was staggering. They had to be perfectly balanced. If the pipe unspooled too fast, the drum would spin out of control. If it unspooled too slowly, the drag would snap the line. They were built in the Tilbury docks, huge rusting hulks that confused any German spy who managed to catch a glimpse of them. To the casual observer, they looked like strange sections of a floating dock or perhaps a new type of boom defense. The entire process of manufacturing, testing, and stockpiling the PLUTO infrastructure had to be disguised. The pipeline was so essential that the Germans could not, under any circumstances, discover the true purpose of the gigantic spools or the massive pumping stations being built on the south coast of England. If the Luftwaffe realized what was happening, a single bombing raid on the pumping stations would doom the invasion's supply chain. The operation became a masterclass in strategic deception. The conundrums were officially described to the press and the public as experimental anti-submarine net layers. But the true genius of camouflage was found on the Isle of Wight and at Dungeness, the jumping-off points for the pipelines. The pumping stations, massive facilities housing powerful reciprocating diesel pumps and centrifugal pumps capable of pushing thousands of tons of fuel across the ocean, were hidden in plain sight. At Sandown on the Isle of Wight, the pumps were installed inside a disguised ice cream factory. The roar of the diesel engines was muffled by soundproofing. Other pumps were hidden inside hollowed-out seaside bungalows, complete with fake lace curtains, painted windows, and manicured gardens. A casual observer, or a reconnaissance pilot flying at 20,000 feet, would see only a sleepy coastal village. In reality, it was a high-pressure industrial complex capable of fueling an army group. A special camouflage unit, Force T, was created to oversee the secrecy, ensuring that civilian access was restricted and that the buildings looked lived in.
By June 6, 1944, the invasion was underway. Operation Neptune was successful, and the Allies secured a foothold in France. But as predicted, the logistical nightmare began immediately. The major French ports, including Cherbourg, were heavily defended. When Cherbourg finally fell at the end of June, the Germans had done their work well. The harbor was a wreck of sunken ships, booby traps, and mines. It would take months to bring it to full capacity. The initial Allied push across Normandy had to be supplied using temporary, vulnerable methods. The famous Mulberry artificial harbors were towed across the Channel, providing a temporary port. In addition, the Allies used tombola lines, short pipes run from tankers anchored offshore to the beach, allowing them to pump fuel without docking. But then disaster struck. On June 19th, the Great Storm hit the Channel. It was the worst storm in the Channel in 40 years. It destroyed one of the Mulberry harbors completely and severely damaged the supply chain. The flow of fuel slowed to a trickle. Tankers couldn't offload in the rough seas. On land, the situation was becoming critical. General Patton, whose Third Army was ready to break out and race for Paris, was famously screaming for gas. His tanks were advancing so fast they were outrunning their supply trucks. The Red Ball Express, a massive truck convoy system, was established to bridge the gap, but it was burning huge amounts of fuel just to deliver fuel. The tyranny of distance was choking the advance. The order was given to activate PLUTO. It was no longer an experiment, it was a necessity. The first phase, Operation Bambi, involved laying the HAIS cable from the Isle of Wight to the Cherbourg Peninsula, a distance of nearly 70 nautical miles. It was a harrowing operation. The first attempt failed when the escorting destroyer caught the cable with its propeller, severing the line. The engineers watched weeks of work sink to the bottom of the Channel. But they persevered. On August 12, 1944, a tugboat successfully laid the first line. On August 22, 1944, a second line was attempted. This time, the HMS Latimer laid the cable perfectly. On August 27, 1944, the pumps on the Isle of Wight were engaged. The pressure built. The gauges flickered, and miles away, in a bomb-shattered field near Cherbourg, clear, refined gasoline began to flow from a pipe rising out of the surf. It was a momentous technical victory. The first physical link between the British Isles and the continent since the Ice Age had been established, and it flowed with petrol.
However, the war moved faster than engineering. By the time the Cherbourg Line, known as the Bambi Route, was fully operational, the Allied armies had already broken out of Normandy. They were racing across France at breakneck speed, liberating Paris and heading for the Belgian border. Cherbourg was now hundreds of miles behind the front lines. The pipeline was pumping fuel to a location that was becoming irrelevant. The fuel arriving in Cherbourg still had to be trucked hundreds of miles to reach Patton's tanks. A second, shorter, and even more frantic deployment was necessary. The planners shifted their focus to the Dumbo route. This was the most direct path, across the Straits of Dover, from Dungeness in England to the newly captured port of Boulogne in France. The distance was only 30 miles, but the currents were vicious and the seabed was treacherous shifting sand. This is where the massive conundrums truly proved their worth. As the Allied armies pushed into Belgium, the tugboats towed the massive floating drums across the straits. They laid the lines at a rate of 4 miles per hour, ignoring the rough seas. The work was dangerous. The Straits of Dover were still mined, and German coastal artillery from pockets of resistance could still reach the laying ships. In one instance, a laying ship was shelled, but the captain refused to cut the line, knowing that stopping would ruin the pipe. He continued to steam forward, laying pipe while shells splashed around him. By October 1944, the Dumbo lines were operational, and this is when PLUTO changed the war. Because the distance was shorter, the pumps could achieve higher pressures and flow rates. Multiple lines were laid side by side. Eventually, 17 separate pipelines crossed the floor of the channel at the Straits of Dover. They converged in Boulogne,
feeding directly into the existing French pipeline network, which the Allies were rapidly repairing and extending towards the Rhine. The volume of fuel delivered by this invisible underwater arterial system was staggering. As the winter of 1944 set in, the weather turned brutal. Fog and storms grounded the Allied air forces and made tanker transport across the Channel difficult and dangerous. But beneath the waves, PLUTO kept pumping. It delivered fuel silently, 24 hours a day, immune to the storms raging above.
By VE Day in May 1945, the PLUTO network had pumped over 172 million gallons, nearly 700,000 tons of fuel to the continent. The peak delivery rate reached an astonishing 1.3 million gallons per day. To visualize this, imagine a fleet of large tanker trucks, bumper to bumper, stretching for miles. PLUTO replaced that entire convoy with a silent stream of liquid beneath the waves. The pumping stations at Dungeness were pushing fuel all the way to the Rhine, feeding the armies of Montgomery and Bradley as they smashed into the German heartland. This logistical consistency was the strategic genius of the operation. It bypassed the need for vulnerable tankers that could be torpedoed. It bypassed the need for crowded ports that could be bombed. It provided a steady, uninterrupted flow of high-octane lifeblood directly to the tanks and transport columns of the Allied armies. It is important to note that PLUTO did not save the invasion in the first week. It arrived later than planned, and the early battles were fueled by the heroic, brute force efforts of conventional logistics, the jerrycans and the trucks. But PLUTO sustained the end of the war. It provided the massive reserve of fuel required for the final, fuel-heavy push into Germany. Without the millions of gallons flowing through the Dumbo lines, the Allied advance in 1945 would have been slower, more cautious, and more vulnerable to German counterattacks such as the Battle of the Bulge. When the Germans launched their desperate winter offensive in the Ardennes, they were counting on the Allies running out of supplies. But thanks to PLUTO, the Allied fuel reserves were deep enough to absorb the shock and keep fighting. The Germans, who had successfully starved Britain in the Atlantic and pinned down the supply lines on land, never successfully interdicted the pipeline. They knew something was happening. They saw the activity at Dungeness and Boulogne. But they could not target a 3-inch pipe sitting on the bottom of the ocean. Their U-boats stalked the Atlantic, sinking tankers in spectacular battles, but they were utterly defeated by the simple fact that the greatest logistical challenge of the invasion had been solved not by ships, but by a hidden web of lead and steel. The project cost an estimated £21 million, a massive sum at the time. Yet, when compared to the cost of the ships that would have been sunk, the trucks that would have been destroyed, and the lives that would have been lost transporting that same fuel through conventional means, it was a bargain.